Good afternoon. So let's get started. We have relatively busy agenda, but we might need a bit more time for discussions at the end. Anyway, so this is CFRG Research Group meeting. I hope you're in the right room. As usual, IETF, IRTF note well applies. So I hope you're well aware of it by now. Okay, I think we have a job. We have minutes taker. Anybody in the Java who can relay questions back? Okay, thank you. Okay. In case you don't know, I'm Alexey Melnikov. My co-chair is not present this time, so I think we have a year of alternating co-chairs this year. Quickly, agenda bashing. Any last-minute suggestions to move things around? Okay. Yeah, I'm sorry, it's a bit busy slide. Just a very quick status of documents. We haven't published anything, no new RFCs since Berlin, but we got one document. EDDSA was approved and is not quite an Auth 48, but getting there. We have pack requirements document sent to IRSG, and I need to sort of ping IRSG to make sure it gets actually reviewed and sent further down. XMSS hash-based signatures, it's effectively done. There was some late discussions with Stephen Farrell about applicability statement and exactly what we know is true about properties of this algorithm. I think text was added. Kenny and I just need to double check the document and send it to IRSG for publication, review and publication. We have several documents updated. David will talk about hash signatures later today. Argon 2 was updated. There was no request from authors to do presentation this time. There was some feedback received. We're trying to discuss with authors what the next step is going to be and what exactly to do with the document. Adam is remote today. He will, hopefully he can do the presentation about ASGCM SIV update and where this is. We also have a couple, well, 3 documents expired. One of them is effectively not active, the Safi catalog, but the other one, we are very hoping for web crypt algorithms to be revived very soon. And we might be looking for co-editor if anybody wants to volunteer. Offline is fine, so please come talk to me or send me email. The other thing, so we were talking about crypto review panel pretty much the whole year. We had the first in-depth discussion and asking for feedback in Buenos Aires. And we opened the call for volunteers in August, closed it in September. We ended up with 7 people on the team. I have created a wiki page for the team, so, oh, hold on. It's actually, so as a side note, the CFRG wiki page was on tools.ietf.org. This was recently migrated to track.ietf.org. There is a redirect. And from CFRG page, there is a link to this crypto review panel page. For now, just lists who is current members, the affiliation, and then we're hoping to list the specific reviews and as we go. I think there are sort of several documents that the crypto review panel will be reviewing soon, as some of the working group, research group documents, and there are also some independent submissions that we might ask to review. I think in particular hash-based signature might be a good candidate just to have another pair of eyes. From administrative point of view, I have requested a new mailing list. Basically, just for coordination. It's going to be a public mailing list, but members only, so everybody can see the archive. But it's, I assume people also in the future will be able to send requests directly there. But it's if people send requests to CFRG mailing list, then we'll post to this new mailing list anyway. Yeah, I'm basically waiting for confirmation for the mailing list to be created. We'll see. That's it on the crypto panel. Any comments, questions so far? All right, moving on. Yeah, I think I mumbled my part much quicker than I expected, but next is update from Adam. I hope Adam is ready. Adam, would you like to try to use Miteco to come to the microphone, and I'll try to project you.
Is that working at all?
It is.
Okay. Can you drive the slides?
Yes, indeed. Just
sure.
give me.
I will start prattling on anyway. So GCMSIV, I'll give a quick introduction for those not already familiar. The basic background is that sort of 15 years ago, we would hand people a block cipher and a hash function and say, there you go. And that turned out to work quite poorly. So these days we hand them an AEAD and that works much better. But the problem is that the non-determinism of AEADs is exposed to an explicit input called a nonce. And the ones that we currently have tend to explode very badly when you duplicate a nonce. So with that piece of context and the fact that a lot of large processors these days are shipping dedicated hardware for AES and GHash, essentially we would like to reuse that in a way which is more robust. So great. So the important thing to point out is that this is work by two actual cryptographers, Shai and Yehuda. I am essentially the tech writer for me, but due to scheduling, I'm the person you've ended up with. So some of the questions I may not be able to answer, but anything about the document itself, I should be able to. Next slide, please. This is mostly covering the introduction I just gave. My slides are uncharacteristically verbose this time because I anticipate some problems with the remote presentation. But yes, we want a more robust AEAD, and we would like to reuse, for performance and power reasons, the silicon which is already in Intel and ARM and S390 and power chips. Next slide, please. So the property we want to add essentially to AES GCM, which is the most common current AEAD, is called nonce misuse resistance, which essentially means that if I try to encrypt two different messages with the same nonce, the nonce is supposed to be unique, but if you mess it up, maybe it won't be. Then if I mess that up, the AEAD should not explode. Whereas the current AEADs do explode. They lose both confidentiality and authenticity. Because of this risk, the NIST currently recommends you only encrypt 2 to the 32 different messages with one key when using random nonces. And a recent paper by Bock and others showed that even in TLS, where there is a unique sequence number perfectly suited for use as a nonce, right in front of you, multiple implementations have managed to get this wrong. At least one of them just fixing the nonce and failing immediately and completely. Next slide, please. So the basic summary of GCM SIV is it is AES GCM plus nonce misuse resistance, and this allows us to reuse the building blocks of AES GCM and take advantage of the hardware already deployed. There is reference software from Shai already available. It was originally published in a paper by Shai and Yehuda at CCS last year. The current form is in the internet draft, and an updated paper is coming. Next slide, please. So the brief motivation, I guess, for people who haven't read the draft is we make sort of two changes to AES GCM. The first one is that GHash, the polynomial authenticator from AES GCM, it operates over a 128-bit binary field with the irreducible polynomial that you can hopefully read off the slide. But its bit ordering is frequently a source of confusion. I don't want to be too prescriptive about what bit ordering is correct or not, because that's a very sensitive topic at the IETF. But Polyval uses a bit ordering which is more natural, and it operates over a slightly different binary field, although if you stare at the irreducible polynomial, you'll note it is the bit reverse of G hashes, which is no accident. Next slide, please. The other more important change we've made to AES GCM is that GCM encrypts with counter mode, where the initial counter is taken from the nonce, and that is completely fine in its setting. But if you worry about duplicated nonces, then obviously duplicating the initial counter goes badly wrong immediately. So GCM Civ authenticates the message first, and then uses the authenticator to drive the initial counter. So different messages lead to different authenticators, lead to different counters and robustness. Additionally, plain GCM masks the result of the polynomial by XORing in sort of the encryption of the nonce. If the nonce is the same for two messages, obviously those XORs cancel out, and that's not good. So GCM-Civ encrypts with AES the output of polyval instead, which obviously doesn't cancel out. Next slide, please. So hopefully all of that previous was familiar, because Shai has presented about GCM-Civ previously at CFRG. The updates that have happened somewhat recently in response to working group feedback is that the key schedule to drive the several per message keys that we need is now a cascade. And thank you very much to those in the working group who suggested this. It works well, and it removes some unfortunate niggles that we had previously. We do have a design that gives better bounds in the security analysis and ever so slightly better performance, but it involves us needing 126-bit nonce, which seems too clumsy to be attractive. And so we are not planning on moving forwards with that. So what is currently in the draft is what we are planning on sticking with. Next slide, please. So a brief rundown of numbers from a recent Intel chip. We imagine that GCM-Civ would be most suitable for back-end encryption tasks, and so the 16 kilobyte column is probably the pertinent one. The takeaway is that decryption runs at about the same speed as AES GCM. I think decryption on this chip runs at 0.65 cycles per byte, and for plain GCM, and for GCM-Civ it's 0.66. Encryption, because of the additional serialization that I explained previously, where the authenticator is necessary before you can start encrypting, runs about 40% slower. It's a bit more for 128 and a bit less for 256. But that is essentially the cost of M1's misuse resistance. Next slide, please. So the next steps, the updated security analysis is still coming, and hopefully will be published before the next CFRG meeting. We have, as I said, reference code published on GitHub. I would like to get it into Boring SSL and get some real-world experience with it. And step 3 is published as an RFC. Hopefully that was brief. And any questions, please?
Hi, this is Yoavnir. I'm channeling someone from the Jabber room. RFC 5297 has all the cryptographic properties you describe. How is this different? And 5297 is a synthetic initialization vector authenticated encryption using AES.
Off the top of my head, I'm not sure I'm going to give a correct answer, but I think the answer is that we can use more AES GCM hardware, and so we are more performant. So obviously, SIV mode is not new, right? I think it is the use of carrier multiplication and such that is new here.
Okay, and the second question from same person on Jabber. Can this also be used as a deterministic AED scheme, i.e. without a nonce, or is a nonce required?
You can use it as a deterministic AED scheme. You have to pay attention to the bounds, because at that case, the initial counter ends up being random. And so you're throwing random initial counters into 128-bit space. And so there will be a limit on the number of messages that you can reasonably encrypt with a fixed nonce. Whether or not that limit is convenient for your use or not, I'm not sure. The limit should be in the draft if you look.
Okay, and the last one is from me, not from the Jabber room. What is the use case for this? I mean, do you see that being used in TLS? Because AES GCM, as it is, works very well with TLS, and you only need to have a counter. I mean, yeah, you said that there was this survey, and they found some implementations that were broken. These were implementations that were broken on a counter. They couldn't manage a counter. Yes. I mean, how can they manage anything else? I mean, for use cases like TLS and SSH and IPsec, I mean, AES GCM works very well. what is the use case for this?
So, to be clear, implementations that got TLS wrong should use the sequence number, which they will be forced to in TLS 1.3. That is the correct fix for that problem. I do not anticipate this being suitable for uses in transport encryption. The cases where it does seem useful is where in backend processing, you will often have large numbers of independent encryptors, all encrypting large amounts of data. And at the moment, you want to use AES GCM because of its performance and power on large chips, thanks to the hardware support. But then you end up with an excruciating analysis about the probability of n-once reuse, and do you try to pick them randomly, at which point the bounds are troublesome. It's not that much data. Or do you try to sort of assign them and come up with a big system of dishing out unique nonces to different computers? And if that ever goes wrong at all, the whole scheme falls apart. I think it's in situations like that where this is useful.
Okay.
Thank you very much, Adam.
Hi, David McGrew. So I have a question and an answer, and if I could just comment on the the previous question. It was a great question. How is this different than the original SIV mode of operation? And so it's more amenable to pipelining and parallelization, right? It'll go faster or take advantage of the hardware design to make GCM go fast. Is there another question? Is there a follow-up, Yola?
Yeah.
Should I let you go next?
No, sure. So another question from the Jabber room. Deterministic AAD is an AAD invoked without a nonce at all. So again, the question is, can this be used as a deterministic AAD?
You can make it one by just wiring the nonce to 0, essentially. But as I said, you've got to pay attention to the bounds in that case. You can't encrypt a vast number of messages.
Sure. Sure. So, I think this is great work. I'm really glad to see this. Thank you, Adam, for, bringing this to the CFRG and working with Shai. So my question is, who's adopted this yet? I mean, is there boring SSL implementation yet? I think it's a practical scheme for TLS. I'm sorry. I think it's a practical scheme. I'd like to see it at any protocol that's essentially not baked in hardware, right? So, GCM was originally designed to go really fast in hardware, and for something like IEEE MACsec, it's great. That should do GCM, but for something like TLS, this is a better scheme. It's more robust against all sorts of misuse.
So
what are the plans to go forward with TLS?
I have no plans to put it in TLS. When I say put it in boring SSL, I mean in the underlying crypto layer to be available for people who want to use it for non-TLS schemes.
Okay, so hopefully we can, CFRG can work with TLS working group on, what an actual implementation would look like and get some real experience with it.
Eric Squirla, for the reasons Adam indicated earlier, I'm not super enthusiastic at this for TLS. In 1.2, right, you had free discretion to choose the nonce any way you pleased, which meant you could make a mistake. But in 1.3, the nonce has to be derived from the record number. So if you're mismanaging the record number, you're going to run into problems extraordinarily quickly. I mean, you won't be able to interrupt, basically. So I'm less enthusiastic about incurring effectively, a 50% overhead in encryption for implementation, which I'm trying to, no doubt I will regret these words someday, but to prevent error, which as I say, ought to be detected extremely quickly the minute you try to talk to anybody else. Perhaps Adam feels differently and thinks I misapprehended the situation, but
no, to be clear, I agree entirely with Eka. I have in mind non-transport use cases for this scheme.
Hi, David McGrew again. So, Eric, you're absolutely right there. people who don't implement things correctly put a tax on everybody else because we have to make our crypto more robust. But there are failure modes like in a virtual machine, when somebody has does a full snapshot and then clones a new VM from the old snapshot. You need this kind of robustness. So that's something that you can't defend against. You can have your TLS implementer do everything exactly right, your crypto implementer do everything exactly right, and then the person who cloned the VM is the person that screwed everything.
Okay, you're on your channeling Jabber again. AES-SIV was presented to TLS back in 2007, and the reaction was, we all know how to increment nonces. This isn't necessary.
Any other questions, comments? All right, thank you, Adam. All right, good. Yep. Oh, yes, sorry. Hold on. Shall I?
Full screen, please.
Control-L.
Control-L. Good afternoon, dear colleagues. Stanislav Smashlev, CryptoPro. And I intended to do a short talk about our draft of internal rekeying, but the chairs asked us to make it wider, to talk about some background, about some motivation, and about related work. And so we'll start with motivation. If we use any symmetric key, we always have to limit the total number of blocks that of plain text that is used with this key directly. This number, say L, can be chosen by trivial combinatorial properties, by Bose paradox and such stuff, by some consideration related to the used block cipher. If we use some vulnerable block cipher, we understand the total number of plain text blocks, pairs of plain text ciphertext that is needed for adversary to mount an attack. So we can limit L with a value depending on these estimations. And the most restrictive ones are connected with side-channel attacks. If we understand that our protocol of our specific software is to be working with in some hostile environment where electromagnetic attacks can be mounted, then we have even more strong bounds that can be uncomfortable if we don't do something special. Anyway, if we have such a bound L, we must understand what do we do after this L is exceeded. So this is the main topic of this talk and this team. First, of course, it can be a trivial solution, just to start a new life, to create a new key, make a new key negotiation, key establishment. And of course, it's a good solution if our L is quite big, then we don't have some problems with performance. And if we can reuse our previous asymmetric key pairs, it's an okay solution, but it has to be studied within the protocol, so it's not the main topic of this talk. It's just a good solution, but not about the rekeying. And if we do want to make something really fast, and if we have some strong restrictions on our L, then there can be two different classes of solutions. First class, we'll call it external rekeying. It's connected with KDFs, key diversification, key derivation, lots of names. So the idea is simple. You just use as an initial key as a master key. You derive your section keys from this key without explicitly using the original key. And then for each derived key, you choose your new IV, or maybe it's chosen automatically. You start a new MAC, you start a new header, etc. So you start a new session with symmetric keys for some set of messages. This is one of the schemes on the slide, which is a parallel variant of KDF. It is the first variant in NIST SP 800-108, KDF in counter mode. There's also two more variants, KDF in feedback mode, that is like a serial variant of the first one, and double pipeline iteration mode. It is quite close to standard construction of deterministic PRNGs when we use some secret state, and then we use this state to make the final keys. In TLS 1.3, the same technique is used. There's a very wise and good solution of making key update. It uses traffic secret N as a secret state and uses the final HKDF to produce the final keys. So this is a sort kind of solution. And it was quite good studied in the work of Abdallah and Belara. The second variant of class of KDFs in the work, serial variant, is just the case of TLS 1.3. And for both variants, for parallel one and for serial one, the full, complete, and correct proofs of security of the fact that the lifetime of the original key drastically increases independently of the encryption modes are presented in this book. It's a great paper, and it closes a lot of questions about the security of KDFs. One more remark here: if we have really strong really strong restrictions on our L, so we can have problems even with the number of operations with the master key when derivation. In such a case, we can use key tree. It's a solution that is also presented in the cited NIST SP. So we just have some levels of keys, and in the final level, there are keys that are used directly for encryption. If we use such a key tree, we can have incredible amounts of reusage of the root key. On the slide is just an example of a key tree. So, which are the advantages of this approach? Of course, the main purpose of this approach is to limit the material to be encrypted on each derived key, and this property is well analyzed, and it's okay with this. The adversary cannot combine information from different sections, from different section keys, and even if some section keys are leaked, then it has no impact on other derived keys. So if some keys are leaked, that is not a problem for a master key or other keys. And the big plus of this approach is that the mechanism can be chosen independently of the encryption mode. Which disadvantages do we have here? For such protocols as TLS, for example, there are no clear disadvantages, and the solution in TLS 1.3 is quite good for that. But for other solutions where we can have encrypted both very short and both very long messages, and if we don't know beforehand the size of the message, it can be a problem that even for extremely short message, we have to get one more PRF. We must mount one quite difficult operation just to obtain the key, and this operation is not needed, in fact. And the second problem is when your L is quite short. If you have very extremely short L, say some kilobytes, you have the problem that you have to finish a message, maybe choose a new IV, maybe start a new GMAC session, maybe start with a new header. So you have to limit the message size also, and it may be not inconvenient for a lot of applications. So can we keep the good properties of external keying, but obtain also the properties of making it effective also for short plain texts and make it transparent. So give us an ability not to stop the encryption and start it one more time. Maybe for concrete certain modes of operation, say for CTR. So we go to the second part about the internal rekeying. The idea here is that during the encryption, after some size of section, we perform function f on our section keys and on our state or IV or chain block, it depends on the mode, and then continue with this key. So it's an extension of the basic mode. And of course, the total size of plain text encrypted with one concrete key is limited by our L. For example, in our draft for CTR and GCM modes, there are two mechanisms presented that use the same block cipher E. It's made for efficiency, so if we already have initialized primitive E with KKI, we just reuse it. And since we reuse the same permutation, we have to provide the property of non-collisions. So we limit our material for a half of the initial one. If we have C-bit counter in our variant of CTR, then we have initial limitations on 2 to the power of C, and this here we have them halved. So here are half of 2 to the power of C. It's done because of the first bit of the second part of the block in constants W is fixed to 1, so that we never have the same constants in the counter sequence in the process of encryption. So we don't have any problems for that the same permutation is used both for key changing, rekeying, and for the encryption itself. And of course, constants are pairwise different. Of course, it has immediately two disadvantages, obviously. The first one is evident. If some section key is leaked, then all following keys also get leaked. So we don't have backward security here. The second disadvantage is less obvious, less evident. There can be some examples constructed that the mechanism mustn't be chosen independently of a mode of operation. If we choose some fixed mechanism, we always can construct some maybe theoretical mode of operation which will be insecure with this type of internal rekeying. So it must be combined together. And which advantages do we have here? First of all, the same one as with external rekeying. If we have quite long messages, it will be a good performance. Also, we have no additional operations here, even for short messages. So if your message is quite short, you don't have to do any permutations before L. So the key is changed when and only when the key change, the rekeying, is needed. You don't have additional unnecessary operations here. And the second advantage in performance is transparency. So we don't need to restart the encryption with maybe new IVs, etc. After each rekeying. So if our limitations on L are rather strict, we don't have problems in logic of our protocol or in our software. And to talk about security, the first advantage is evidence. It's like in external rekeying, we can limit the total size of messages that is encrypted on one key directly. And two, they are blue here, advantages that the adversary cannot combine information from different section keys, and the total left time of initial key drastically increases, like in external rekeying, of course, they must be proved, as they are not evident. A few words about the proofs. Again, these security estimations must be done with the concrete particular encryption mode. It must be done with knowing the properties of this mode. So we have, in fact, a new mode of operation that is combined basic mode with rekeying. And so we use the same model as for modes of operation. It's lower CPA, like in work of Belare and Rogovay. It's the same GMAC. For the basic block ciphers, we use standard notions of PRF, PRP into variants. So the results here are quite long, and to be more understandable, one concrete example: if our block cipher is secure, so if its estimations of security in PRF, PRP, and CPA and CPC models for the basic block cipher are default, so it's not broken, then you have the following bounds on CTR and CTR with key meshing, with rekeying. So the total lifetime of the key increases quadratically. So we have m and mn square for the probability of the adversary to attack. So we really have this increase as we hoped. About the performance, I think I'm short of time, so maybe just a few words. Even if we have quite strong restrictions like 64 kilobytes or 500 kilobytes, we have about 1 or 2% of decrease of performance when using AES 256, and even less if we have AES with 128-bit keys. So performance it's also quite okay, but it's because of the same permutation is used. One last comment: these two approaches are not rivals. They can be combined in a good way to eliminate the problems, the disadvantages of each other. If we have our external rekeying made on some large sections, say of some number of messages, and internal rekeying is made with some smaller L, then we at first don't have a disadvantage of internal rekeying because we don't have all keys leaked if one section key is leaked. The effect is limited. And secondly, we don't have a disadvantage of external rekeying because we don't have any problems of limiting the message size. And we don't have to make a big key tree, key hierarchy here to move on if the restrictions are very strong. So the summary: both of variants, external and internal rekeying, can help us to obtain good bounds of usage of any keys that is applied to data explicitly. Both of them allow us to increase the lifetime of a key drastically, and both of them provide forward security. But the differences are that the internal rekeying doesn't provide us backward security, and external rekeying doesn't provide us an ability to be comfortable if our restrictions are quite strong. And it leads us to using unnecessary operations on extremely short messages. And if we combine these two approaches, then we can, even in case of very restrictive L, we can obtain a mode that doesn't have all these disadvantages. Open questions here. First of all, theoretical question. We had a personal communication discussion with Michael Belair about these ideas. He found it quite interesting, and our opinion with him that this method can be applied to a large class of schemes for CFB, OFB, etc., and maybe even without additional keys. In the scheme we proposed, we don't have additional keys for rekeying, so only the initial key is used. And the question of finding a large class of schemes for such for another methods may be interesting. And the second question is from me myself. In our proposal, we chosen to use the same encryption operation for the rekeying. It was done by thoughts about performance, but if we use, for example, some hash here, we can lose not much performance, but we can obtain modes for CFB, CBC, for example, more simpler. And I think it can be discussed. And the most important question for us is that do we need a CFRG draft, a document, and maybe RFC later, with various rekeying techniques in one draft, existing and new ones? Kenny Patterson suggested thinking about creating such a draft. So we have a menu of choices for developers to choose a rekeying technique that is good for some perspective protocols. I fully support his idea, so if this work is to be done, of course, I'll be very glad to be involved in this work. That's all. Questions, comments? Thank you very much.
Hi, David McGrew. I have a question. So the really interesting thing, in my point of view, is the possibility of resisting side channel attacks by having leakage resilience. Right? There's a small but interesting literature in leakage resilient encryption and MAC schemes. But let me ask about this work in particular. Is it actually analyzed in the bounded leakage security model? Because is there an actual proof of security in that model?
Thank you very much, David, for the question. It's a great question because it's just the work we are doing now. We have two results on in the models that consider side channels, and these results are, I would say, some maybe first half of all the way. So there are quite difficult properties to analyze. We have some positive results here, and the other half is just intuition. So yes, this work has to be done. Of course, to change key is always, if you change them wisely, is always better than not to change these models. But of course, all transformations, including using hashes for transformations on the basic encryption to transformation, must be analyzed very thoroughly. It's very important, and yes, it has to be done. I didn't cite results here because they're not published, and we could make some preprint, but these results are only part of the whole way we should go around. If you could be involved in this work, it will be very good. You or someone else.
So just an observation on the motivations for work like this. Internet of Things cryptography desperately needs side channel resistance, right? So I think that's, you occasionally hear people talk about, IoT crypto, and it needs to be special, it needs to be lightweight, it needs to be side channel resistant. So that's a shameless plug for IoT there.
Thank you.
Any other comments, questions, anything in Jabber? All right. Thanks, Stanislav.
Okay, thank you.
Yeah. If you want, you can use this. Hold on. Let me just. Just, yeah, take it and, yeah, hold it in your hand.
Can you hear me well, everyone? Okay. So today I'm going to talk about secure MAC algorithms. There's something wrong. Secure MAC algorithms for use with NTP. So what is NTP? NTP is one of the oldest internet protocols that is used to give time to computer systems on the internet. So this is how an NTP packet looks like. There's something wrong with the display.
Is it doesn't fit or what?
Yeah.
Oh, it might be just a problem with my resolution on my screen.
You won't be able to see the headings though, so that's fine.
Sorry.
You're good?
Well, if you want, I can just go through slides in the Open Office. It's lower resolution, but it might fit.
Yeah.
Okay. Let's try this. That's, oh, hold on.
And it still doesn't fit, I guess. It's okay, I guess. I don't think I have a choice. Okay.
Or just the full screen then.
Yeah, so this is how an NTP packet looks like. Currently, how NTP authenticates its UDP traffic is by concatenating this message digest, 16 bytes of message digest at the end of the packet. So RFC 5905 suggests using MD5 for NTP authentication this way by key concatenated with message. And why is this bad? I guess I need not to state. Everybody knows MD5 as a hash function is not collision resistant, and it's vulnerable to length extension attacks. Consequently, RFC 6151 says not to use MD5 for authentication this way. So in this draft, we propose some secure MAC algorithms that can be used for NTP, keeping in mind specific NTP constraints. And we analyze the performance of various MAC algorithms. So these are the potential algorithms that we consider. We try to have a combination, a mix of different kinds of algorithms. So there are a couple of hash algorithms, and then we have CMAC and GMAC. They are block cipher-based algorithms. And we use, this table contains legacy MD5 and HMAC MD5 just for the sake of it. And then we have this, so we choose these algorithms because they have the same, based on the same key input length and the same output key lengths, so that they give the same security. Like the security level of these algorithms is upper bounded by this key length and the maximum of the key length and the output length of the tag. So these are all comparable in terms of security. And now we analyze the performance of these algorithms. So in terms of performance, there are certain specific constraints to NTP about the kind of crypto that it can use. So first is it requires constant computational latency. The fewer clock cycles are better because this directly translates to a reduction in the variance in the latency. And second is the throughput. Since NTP servers deal with thousands of requests per second, throughput is an important factor while considering crypto. For instance, NIST that maintains most of the Stratum 1 servers, NTP Stratum 1 servers, it caters to approximately 28,000 requests per second per server on average. So throughput is another important factor that we consider. We consider two factors, latency and throughput. Now these NTP servers run on various kinds of hardware and software platforms. So we consider several different platforms. The most popular being Intel, which also has custom support for AES. So we do analyze performance for both with AES, this new instruction set enabled and as well as disabled, and we see that GMAC performs better than our legacy MD5, of course, because of, and it's better on when AES instruction set is on compared to the other, and these numbers are closely followed by CMAC. So these are the two best ones that we could look at. This shows the latency in terms of number of CPU cycles per byte that it takes for a 48-byte NTP payload to get authenticated. This is the GMAC is the authentication mode for GCM, that AES GCM that we were talking about earlier, and CMAC is a block cipher based MAC. We also perform tests on some other platforms. And these are the 4 platforms that we perform these tests on. And again, GMAC has the best performance, nearly best performance in all of them, closely followed by CMAC. And although HMAC MD5 performs, HMAC MD5 performs better, but we don't consider it because it's not secure enough. So what are since we saw that GMAC numbers are the best, but there are certain NTP-specific constraints that we cannot use GMAC on NTP. The first point is NTP servers are stateless, and the second is that the key that is used by NTP servers is shared by many servers, typically the servers at the same stratum. Now, why is this a problem? I'm not sure if I should explain it because it has all been talked about now, but so there is this problem with GCM mode. We know that it's nonce reuse vulnerability of GMAC. One can recover the entire authentication key, even if the nonce is repeated once for the same key and different messages. Nonce length is 96 bits. Because there's this customized implementation for all these fixed parameters that the GMAC gives us good performance, so we cannot change these factors. And there is a high probability of collision for the nonce after 2 to the 48 messages because of the birthday bound and NIST documentation. No. Yeah, so the number of messages that can be authenticated is limited to 2 to the 32, just to be on the safe side. Now, NTP server is stateless. It does so after 2 to the 48 messages. The key should be changed because there is a high probability that nonce will be reused. However, the NTP servers are stateless. They don't know when to refresh the key, and this becomes a problem. Even if the server keeps the state, 2 to the 32 is a good number of messages. However, an MITM can easily replay these messages and exhaust this number really fast. And so the server has to reissue or re-exchange the key quite frequently, which is not a viable option for NTP servers. Even if the client keeps the track of number of messages, again, an MITM can easily replay messages and exhaust this number. So there is no way we can keep a track of the number of messages. Like, we can keep a track, but it can be easily exploited. So what we recommend is, as we've seen, GMAC performs the best, but has the weakest security. HMAC doesn't give us a good performance. However, the security is good. CMAC seems to be a reasonable choice, and it has less implementation pitfalls, as we have seen so far in the literature. There are other potential MAC candidates. There's this new IETF draft for network time security by Daniel. He's sitting here, and he suggests using AED mode, use AES CMAC with SIV, because we need an AEAD instead of just the MAC for NTS because of the privacy issues. We want unlinkability property for the client when he moves between the networks. So we need an AEAD just instead of just the MAC. And this SIV mode is robust against accidental nonce reuse. Another option is GCM SIV. We've heard enough about it. It's nonce misuse resistant, and we performed some performance analysis, and its performance is in between. It stands somewhere between GMAC and CMAC, but it's still an internet draft, and it's not widely implemented. Because a part of the reason for choosing these algorithms was they are standardized and widely implemented, so it will be easy for deployment. Then there is another option, SIP hash. It claims to be a pseudo-random function. It is optimized to work with short messages, but we have never seen any IETF draft RFC for it or any pushes. Or there are, I couldn't find at least a lot of implementations for it. So if anybody knows more about it, we can talk and discuss. And then there is another Caesar AD competition going on where there are several proposals for nonce misuse resistant algorithms, which we can look into. But it's gonna take a long before it gets standardized and implemented. So I have a few questions for CFRG before you start questions. Is there a better option? Like we suggest CMAC, but I would love to hear if there are other options, or can we use GCM or GMAC in a way that is nonce misuse resistant? I talked with Kenny, and we tried to tweak GCM a little bit, but then performance degrades because it is so customized for its fixed parameters that it is hard to change anything. Any other insights are welcome. Thank you. That's it.
Questions now?
Yeah.
Hi, Kyle Rose. For the analysis of GMAC, did that include the cycles required to generate the random nonce? Okay.
Yeah. Just to add a little bit of context for the benefit of Becker and anybody else here who has been following the network time security effort. The context of this presentation is an effort that is related but separate from NTS. So the NTP working group is embarking on a rather extensive effort to add support for a TLS-based handshake to secure NTP. However, what the symmetric crypto that NTP supports now, as Anshul pointed out, it's less than satisfactory on account of the MD5 KPN value construction. So we're looking into some people are not going to want the complexity of NTS and just continue using symmetric crypto. So this is an effort that's more limited in scope to just swap out that awful MAC with something modern and reasonable.
Yeah, I mean, this seems like good work. I don't immediately see any way to fix GCM for this scenario. I guess I'm a little surprised. I mean, the numbers you seem to be reporting for cycle per byte, like CMAC, seems completely acceptable. So, I mean, I guess this is like a situation where I would choose the simple thing rather than getting fancy.
So, Martin Thompson, it was unclear to me from the start of the presentation whether you were concerned about simply how many messages you could process, or whether it was the time that it took to generate the MAC was adding enough extra delays that was having some measurable impact on the accuracy of the time that you were getting.
It does.
Which? Do you want to process more messages, or do you want to spend less time after you've created the message doing extra work?
We need both for NTP.
Yeah.
We want to create, at least a reasonable number of messages with the same key. Yes. And then we need sure the latency should be less.
Yeah, because most of your numbers talked about how long it would take to generate the MAC.
Yeah.
Whereas if you actually know how long it takes to generate a MAC, and most of these things are constant time, you can account for that half of things.
Yes, I guess most modern implementations do constant time.
I'm not aware of any that don't. So
because we tested on OpenSSL and LibreSSL, and I guess they are doing.
If you pick up a crypto library, all of these will be
not necessarily
encryption in constant time, isn't? Oh, okay. Yeah, I believe most of them are.
They should be, but I'm not sure if they are.
Yeah, but in any case, you didn't present any numbers on the jitter that you were seeing, the variation in time that it took to actually generate one of these things, which would have been interesting to sort of learn, because that tells you whether or not it's practical to account for the time that you've taken to generate the MAC.
Okay. Any other questions? No. Thank you. That was very interesting. Thank you. Yeah, that's fine. Just give it to David. You're next. Just hold this, and you can hold this, but I'll just load your slides.
Thanks. So I'm afraid you have to hear about post-quantum cryptography now. And you know, post-quantum cryptography is making cryptography great again.
Oh, yes.
Yeah, I wasn't in the U.S. during the election. It was that was some interesting news. So thanks for the opportunity to talk to you again today. I'm going to give an update, kind of an extended update on the hash-based signatures internet draft. And then I'm going to talk about something new and completely different, which is batch message signatures. And so this is joint work with everybody I could rope in: Scott Fluer, Michael Curcio, and Panos Kampanakis. Oh, I guess I control the slides. Here we go.
Sorry, it's a bit
Oh,
bottom, but
it's getting cut off.
Oh,
that'll be interesting. So let's see. So the quick recap on hash-based signatures. What's good about them is that they rely on only one security conjecture, and it's a really basic conjecture, right? That your attacker can't invert SHA-256 in this particular case, and it could be post-quantum secure as long as you don't truncate your SHA-256, right? So post-quantum security is pretty easy to achieve. That's a great thing. The bad thing is they have big signatures and big key generation time, and also stateful signing, right? So there's some downsides that we need to engineer around. There's some ongoing standards development I wanted to mention. So I'll talk a little bit more about what's going on in CFRG outside of this particular draft. NIST has decided that they don't need to have a special, they don't need to include hash-based signatures within the scope of their post-quantum secure cryptography, because they feel that you know, there's already groups like CFRG that are actually looking into this area. So ETSI is also interested in standardizing that sort of thing. So we've some people from ETSI have talked to us about that. So this is the standards landscape. So let me give a real quick overview. If you're not familiar with hash-based signatures, it's possible to build a one-time signature that relies on the fact that a one-way function can't be inverted, right? So you make up some random values, you apply the one-way function to each value independently, and that produces the key. And then, you know, if you're clever, there's some combinatorics about how you map things there, but it's pretty simple. And what you end up with is a scheme where the signature will be something like 2 kilobytes. You have a single private key and a single public key, and you can sign one message with it. And then, since we work in computer science, we solve every problem with a tree. So if we want to sign a lot of messages, we can make a lot of one-time signatures, and then we make the Merkle hash tree out of the public keys, and that gives us something like, it gives us a scheme like this. The red is supposed to indicate that's a private key, and the yellow is a public key. And there seems to be a real formatting problem. That should be 2 to the power 20 signatures. No, is that right? Yes. So this would be about 3 kilobytes in the middle, right? So we've got a bigger signature, but we can have a lot more messages, but our key generation time goes really big. And then, so we want the ability to sign lots of messages, but we want our key generation time to not be astronomical. So we move to this hierarchical scheme on the right. And so here for 2 to the power 40 signatures is going to require something under 6 kilobytes, right? So we've got this hierarchical scheme where what we've done is we've taken the scheme in the middle, and on the right, what we're doing is we sign the public key of the lower level with the one of the private keys of the upper level. So whenever we run out of signatures at the bottom level, then we just generate a new tree for the bottom level and then sign it with the next thing across. So you can actually build a practical scheme out of this. And for this particular draft, the hash-based signatures draft, my apologies for the formatting weirdness here. The thing on the left is called the Leighton-Macaulay one-time signature scheme. In the middle is the Leighton-Macaulay signatures, and on the right is the hierarchical signature scheme, right? So lots of acronyms. So one of the things we've added in the recent version of the draft is we've addressed some of the problems around state management. And so here's a link to this this work on state management that we did. And essentially what this is I'm going to present some system security issues to you that were addressed in the most recent version. So with a scheme like this, you have to carefully manage the state. If you're I should explain, if you're creating the signatures, you're signing messages, then you have to carefully manage the state because each one-time signature corresponds to a single message. So you'll have a process that looks something like this. You get a message in to sign, and since you've got some non-volatile version of your key somewhere, you have to actually increment that before you release your signature. Otherwise, you might accidentally double use a one-time signature private key, which would undermine your security completely. So the system security issues are, well, we have a file system cache and a disk cache that are in between us and the actual non-volatile copy of the key, and that's something that we need to deal with. So the recommendation, and actually there's a requirement in the draft around this now, what it forces the implementer to do is to reserve keys, right? So we call this the reservation operation, that essentially you look ahead by capital R keys, and then you keep those in the volatile memory, and it improves performance because you don't have the latency of writing the disk and getting a confirmation that you've written a disk, and it also makes you more robust against synchronization failures that might occur. Say again? So there's a very easy way to implement this recommendation that I just described on the previous slide in a hierarchical signature scheme. And so this is what the draft says, is that with your hierarchical signature scheme, on the top level, the private key has to actually be stored in non-volatile memory, right? Because you need a non-volatile copy of your private key. But the leaf level needs to be volatile. So this, and what we mean by volatile, of course, is it's never written to non-volatile memory. And so this is the same as, let's see, reserving all of the private keys down there. So anyway, this avoids the issues that I mentioned earlier So there is a problem that it doesn't address, though, and the problem is unintentional cloning. So, in the modern, computational environment, you have, somebody writes an application, somebody else writes a container, somebody writes an OS, somebody's got a VM, and it turtles all the way down, right? So you never know if somebody's actually going to clone your virtual machine or make a copy of some state as part of some bigger virtualization scenario. So if there's a backup or a system snapshot that makes a copy of a private key and then restores it and runs it, that's a problem. And this is a problem that's not addressed by the current draft. Any stateful scheme is going to not be secure in this environment. So there has been some academic work in this space. Sphinx from Eurocrypt 2015 is a purely stateless hash-based signature scheme. It also has huge signatures, like 45 kilobytes, right? So it's like a factor of 10 bigger, and a very large key generation time. So one of the goals of the current version of the hash-based signatures draft is to add an option to provide some protection against the cloning attack by allowing the top level or the root level to be stateless. And so this is not specified in the current draft, but one of the motivations for the reason we reorganized the hierarchical signature scheme in the current version of the draft is so that we would future-proof the specification. So we're not trying to define this in the current draft, but we made the changes so that we could come along in the future and specify this thing, which was be a hybrid signature scheme where we have the leaf level is stateful and the root level is stateless. There are some stateless schemes like the hash of random subsets that are practical. And so this hybrid scheme actually has a number of appealing properties to it. And it looks like Tero has a question.
Yeah, this is Tero Kivinen. One of the things I think I talked about you earlier was about this making the top level to be time-based. So to pick up one of the, because you have lots of one-time signatures and you pick one, you pick them by order, but you could actually say that, okay, this first one is used for this amount, this time, and the next one is for that time, and so on. So when you boot up, you look at the time, and then you pick up where you are. So you don't have to store anything in the disk, because from the time you know which signature you're going to be using. And then you have to just make sure that, okay, you don't, what the time limit is going to be, how many of those you have, and then you pick one of those. This actually might work also for the NTP stuff that I've been using, for example, the last presentation of how to generate the nonces, because they have very good time in the NTP.
They should.
But I mean, in that case, it would be actually allow you to, even if you clone it, when you restart it, it gets a new time, because otherwise, nothing works if your time is correct. So you want to, then it would be pick a new, signature at that point.
Yeah, I think that awareness of time and incorporating time in a scheme like this can definitely improve security, and in particular, the willingness to abandon a private key because that was Monday's key and it's Tuesday or something like that. That looks like something that would be a valid strategy for both stateful and stateless, I think.
Daniel Franke here. A time-based non-scheme would absolutely not work for NTP because the supposition of NTP is that you don't already have good time. That's why you need to run this protocol. So there would be a clear chicken and egg problem there.
Yeah, so this isn't the NTP session, though. But that's a good comment. Thanks for making that. So let's see. So here's, what I provided was background. Hopefully, clear background. It was a little bit rushed, but so here's the actual updates to the draft, right? So starting with the old history, the draft, the first version of the draft was several years ago. It was based on Ralph Merkel's original work, and it carefully chose from a number of things to make a scheme that was practical. it's not provably secure. The original version of the draft was not provably secure. And in particular, you couldn't even prove it secure in the random oracle model. Let's see, XMSS, the extended Merkle signature scheme, is this other CFRG draft that is more advanced and was actually based on version 3 of this draft, right? So we contributed the text to give them a head start with that. So version 4 of the hash-based signatures draft, the current draft here, made a major change. It moved to be based on Layton and Macaulay's 1995 patent. And there's a fascinating story behind this patent, right? There was never a significant peer-reviewed publication of it, but it was design work to make a provably secure, in the random oracle model, hash-based signature scheme. This was in the context of the original National Bureau of Standards digital signature scheme in the very early 90s. And so this is an expired patent. And I've had I've actually had people tell me, well, you know, I don't like your draft, David, because it's patented. And well, you know, it's a nice thing to implement an expired patent, because then there's a very clear record of the intellectual property in case somebody, you know, claims they invented it last year and now tries to sue you. I'm not a lawyer. I don't give out that advice. So, I don't know. So that's the major change to move to LMS, was because we wanted to be provably secure in the random oracle model. And there's a section in the draft explaining how essentially it's a lot of bookkeeping to make sure that you have a distinct input that for every invocation of the hash function. It's a subsection in the security considerations. So for version 5, we cleaned up a number of things. We made it possible to use a hybrid scheme, so you have a stateless root, and we added a requirement that the leaf level be a volatile level, right? And we made a change. So the identifiers, that's one of the fields in the spec, are now independent at each level of the hierarchy, and that's important for the proof of security. It's something that I botched the first time. And we also stripped out the parameters that are not post-quantum secure. And I actually do have reasons why I'd want to use this, that even if somebody never invents a quantum computer, but we decided to go with the post-quantum security level because it simplifies things. Fewer free parameters. And this isn't actually in the draft, but there's a implementation on GitHub that I wanted to mention. So a quick comparison between XMSS and HSS, the LMS. So hash-based signatures is the bottom one in the comparison. So XMSS is moving to RFC, which is great. I think that's it's great work. It definitely should go to RFC. It's provenly secure in the concrete security model. And Andreas Holzing and some collaborators recently published a proof of security that corresponds to the actual draft, whereas the previous one made some assumptions. There was a gap in the analysis. So they've actually closed that gap, which is really nice. And with the hash-based signatures draft, the way I would describe it is it's evolving to meet the requirements around the need to have a stateless or hybrid scheme. And it's provably secure. There is a published proof that has a gap in the sense that it doesn't apply to the current draft and doesn't cover everything, but it's Jonathan Katz's analysis that he published at the very beginning of this year. And that's in the random oracle model. So as people study the security of resistance of algorithms to quantum computing, we think that the random oracle model won't have any nasty surprises for us. And that would actually make the HSS really appealing. Performance-wise, I think I don't, okay, I do have some performance numbers up here. So the HSS approach is actually better performance-wise because it has 1/3 the number of invocations. Because to be provenly secure in the concrete security model, there's more work to do. And Alfred Menzies did this really interesting publication on when people try to be secure in the concrete security model instead of the random oracle model, they end up doing a lot of extra work. And, sometimes it's well justified and sometimes you don't need it, right? So the reason for having 2 drafts here, I think it's well motivated because the hash-based signatures draft is simple, and if it's secure enough, that would be attractive. But given the level of uncertainty around quantum computing, having 2 drafts certainly isn't a bad thing. The signature size for the draft that I'm an author of is a little bit bigger. Sorry, the formatting is eliminated a column on me, actually. So for the hash-based signatures draft, I'd love to get people's feedback on this. So if you're interested in hash-based signatures or somebody who hates complexity in crypto standards, this is your slide. So there are essentially 3 parameter choices for the hash-based signature scheme. We have a parameter that chooses a trade-off on the signature size versus time for the one-time signature component, a parameter that determines the number of signatures versus key generation time, which is in the Leighton-Macaulay signature scheme, and then for the hierarchical scheme, you get to choose your number of levels. So we actually reduce the number of parameters by making it only post-quantum secure so that you're now always using SHA-256. Obviously, there's other good choices that could go in there instead of SHA-256, but these are the parameter choices that we've made. And it's more parameters than I'd like. And, if anybody has, strong feelings about what needs to stay or simplicity, I'd love to hear that feedback either here or on the list. So we've done several implementations, and some other people have implemented hash-based signatures. And I think it's really valuable that people are starting to get experience with this, because this is the case where, you can be provenly secure in some model, but then you can mess up system security in the real world. And the fact that these schemes are stateful is important. And one of the nice tricks that we came up with in our implementation is the idea of including in the private key format that's stored on file detailed information that's specific to the creation of that file. In other words, like you can see this sample code is getting the full path, hashing it to make a checksum, and then sticking it at the beginning of the private key, so that if somebody makes a copy of a private key, the program will refuse to generate a signature with it. So I think it is possible to implement these things correctly. And I definitely trust somebody who's building a hardware security module to do it right. The tricky bit in the standard is going to make sure that somebody who tries to use it in a general purpose software environment doesn't end up shooting their foot off. So if you're interested, please do check out the implementation on GitHub. Here's the usage statement. I wish I could do a demo. I wanted to show how long it takes to generate keys, which isn't, it's not onerous, it's livable, but it's for larger numbers of signatures, it does get big. And let's see. So as an example of what really happens with a scheme like this, the test code has, let's see, we have the Bill of Rights is the first 10 amendments to the Constitution in the US. And so we have the text files for the first 10 amendments here. And then we generate a public-private key pair called Bill of Rights. And then the script will sign all of the amendments. And you can see this is a time-reversed listing, right? So this is ls minus LTR. And you can see the text files existed, then the public-private key pair was generated, the signatures were generated, and the last file modified was the private key, right? Because remember, this is a stateful scheme, right? So that thing has to be updated all the time. So one of the sticking points in the previous version of the draft was, what the hell is the format of this object anyway, right? Especially with the signatures. So in the code, we have one of the options in the program is to print this output, print the output of any of the objects. So please check that out. Now I'd like to shift gears to batch signing. How am I doing on time? If anyone has if there's a question or comments on the draft, that I just talked about, love to hear them now, or I can talk about the new thing. So let me go on to the new thing, and it's actually not that new, but it actually slots very nicely into a problem. So one of our big use cases is software signing or firmware signing for the hash-based signatures, because we want that to resist all the attacks that will be developed over the next 15 years. And once you start looking into signing all of the objects in a package, say Debian Linux package, you quickly realize there's tens of thousands of these things. They have separate signatures on them, and if you've got an n-time signature scheme, where you have to fix n at the time you generate the key, and there's a cost to increasing n, right? There's a tension between, how big can you make n and how long are you willing to wait for the key. So if you can sign message in batches in a way that allows you to not use up your budget of messages that you can sign, that would be a really attractive thing. So our goal is to make it possible to deal with a lower n, and there's an idea we came up with independently, but was published back in 1999 by Colin Boyd, which is a pretty simple idea. If you have a batch of messages that you want to sign, you can hash those messages independently and then create a Merkle tree from the hash of the messages that you've signed, and then sign the root of that tree. And in the signature format, you just include the siblings on the path between the message that the signature is for. And so essentially, you provide just enough information in the signature that somebody can reconstruct this path. So if you had the example like with Debian, there's something like 60,000 packages. So, with a cost of 16 elements, you could batch sign all of the packages in a distribution. And that's a really attractive thing if you have a scheme where you're limited in the number of messages you can sign to some fixed number somebody had to choose in advance. Question? Right.
I mean, so as you say, this is the obvious design. The other obvious design, however, is to make a manifest file and sign it. And and the only reason to do this is you want to independently distribute the signatures one at a time. But but I mean, if you have I think, right. So I guess there's really nothing wrong with this design, but it's less efficient and more complicated if you want to if you're going to distribute one signature file at the end of the day.
Yeah, absolutely. That's a very valid point. And whenever you're authenticating software or firmware, the question is, when are you going to validate it? And if you can sign let's see, the ISO file, right, for your Linux distribution, that would be an easier way to do it. And then you can verify it once. But then the appealing thing about doing it separately is that somebody can get a subset of those packages and then verify them. And as the packages evolve, they each have separate signatures on them. So
how does that? I'm with you on you can get a subset of the packages, and I can distribute only the signature from the root down to that guy, and therefore I've saved whatever the the megabyte or so of signature data. Manifest data, but I mean, the signature at the top, nothing can change after that signature has been generated, right? The signature is generated on one configuration of the other system.
Right. So what I meant to say was there's some advantages to signing, objects independently.
Yes, I don't disagree with that.
Daniel. So, but the nice thing is that this scheme is actually, very little incremental effort if you already have some code and specification lying around that deals with Merkle trees. So we did not include this in the current draft, but it potentially could be something that would be useful in the future. And as we're experimenting with different use cases for these signatures, if we can get by without this batch thing, then we'll do it. But if there are cases where it really helps us out by lowering the number of keys we'd have to, or number of signatures that we'd have to deal with, then we'll go ahead and do that. So that concludes the overall presentation. And thanks for your attention today. I'd love to hear your comments or feedback if you have any.
Shall we move to the fun stuff again?
So
you have about 20 minutes.
So you know what happens in a volunteer organization when you say something should be done, you get asked to do it, right? So that's why I'm still up here, is that I said that we should talk about post-quantum cryptography. And so there was a really great discussion in Argentina. If I could ask, how many people were present in Argentina? Super. So, I guess I control the slides. Yes. So as far as I'm concerned, right, we've already started the conversation, right? I think, I prepared a lot of slides and asked a lot of questions. I was the discussion leader in Argentina. And so I wanted to reprise that format, right? So I'm not going to make a presentation. Instead, I'm going to try to stimulate a discussion. And the disclaimer is that slides don't represent anybody's point of view. And so I just have 3 slides here that I wanted to go over. And I'd love to get the sense from people on some different topics. So with post-quantum secure cryptography, symmetric cryptography actually, starts to look good, right? Because if you use AES-256 instead of AES-128, you're probably going to be secure against an adversary that has a quantum computer. So that's a really appealing thing, right? Because 256-bit symmetric crypto is available in a lot of things, and it'll be an NTP soon, right? And so this is a question. There's a lot of expertise in this room that tracks different areas like NTP or TLS or IPsec, and there's cryptography shows up in a lot of different things. So I think there are 2 good questions for us to ask in this space. Is there a place where we need standards action to get 256-bit symmetric security level into a protocol? So that's one question that I'm hoping people can respond to. And then the other is, do we need to recommend people use larger keys in order to get people to start actually adopting and deploying the larger key sizes? Right. So 2 questions. One is, do we need standards action? Hopefully we don't need a lot. The standards action to introduce 256-bit security levels. And then the second is, the getting people to actually use it, not just to specify it. So I know there is some action. I think Kerberos is doing this, right? There's a Kerberos 256-bit. Yeah.
Yeah, John Mattsson, Ericsson. NIST has recently decided that AES-128 is quantum secure at their minimum level in their computation. I think they have quite good reasons for that. I kind of agree with that. So I don't know how much focus we should have on introducing 256. It's no panic to do so. It's more a theoretical concern than any practical. No quantum computer ever will basically break AES-128.
So I hope that's absolutely right. And I'd love to hear what other people think on that.
Do you, Eric or Scarlett, do you have a survey of which protocols actually would need? So there's two things here, right? One is documenting how to use 256 with a new protocol, and the other is, saying you really ought to use 256, right? So
right.
At least I know apparently Kerberos and TLS already support 256-bit AES, right? So do you have a survey of which protocols would actually need standards action, or is that the question you're asking on the slide?
It's the question I'm asking. No, I don't have a survey.
My impression was SMIME did. I don't know. Sounds like you all might know. IPsec?
Well, IPsec has it, TLS has it, but beyond the protocols themselves, in any product, in any browser that you record the client hello from, it has AES-256. Any IPsec implementation that I'm aware of has AES-256. I think by now it's a moot point of whether we need AES-256 or not. It's just there.
Good. So, good. I was I was fearing that somebody would stand up and say that they had a particular case that they knew of where standard action was needed, but it sounds like that's not the case.
Yeah,
Super. Comment?
Ben Kadek. So Yoav's comment about particular products reminded me that a lot in at least the Kerberos world, people do have trouble when they're using the Java Kerberos implementation because there's a separate add-on you have to install to get the 256-bit crypto module.
So let me take John's position for a little bit, which I think we all agree that with the currently available information, AES-128 is far stronger than essentially any elliptic curve or finite field algorithms we have available to us, right? So under that understanding, as long as you have a protocol which is based on public cryptography for key establishment, there's really no point in doing anything here up until the point where you also have a post-quantum safe key establishment to go along with it, right? Am I misunderstanding the situation?
I think if you have a protocol that incorporates both symmetric and asymmetric, then you're absolutely right. If you have something like TCP/AO or NTP-MAC or something like that, then you'd be purely symmetric, and then you might as well use a big key with your.
Well, I guess. So I guess now that's got really complicated because the typical rationales for our discussions about post-quantum have been about under the assumption that not that there's a covertly existing quantum computer currently present, but that there is the potential for a quantum computer to exist in the future, and we're trying to harden ourselves against that situation. And so the protocols you're referring to, of course, are integrity-only protocols, which only are threatened when the quantum computer exists, as opposed to retrospectively. So, and of course, I think my understanding is at least that nobody uses AO, and that the people who are using NTP are talking about using public key exchange anyway. So you're back in the soup. I guess my suggestion would be to make a narrow recommendation, which would be to say, if you're using a post-quantum key exchange or otherwise do not have to worry about the weakness of your public key algorithms, then you should consider using 256. And otherwise, probably 128 is fine.
So that's a really good point about the protocols that I mentioned, right, which are not the first sort of thing you think of when you think of internet cryptography, right, are authentication only.
Yeah. Hi, I'm Quinn Danganes, and thank you, David, for started the conversation again. And NIST really would like to encourage the community to work harder on post-quantum crypto, and we plan to finalize the call for proposal in November. So hope everybody keep an eye on that, and hopefully we'll be done in November. About quantum security. in the recent discussion, internally at NIST, and we started questioning, we don't really know for sure what is quantum security. For example, if a quantum computer, the speed is like the normal CPU right now, then AES-128 is not good. But, what is likely for the quantum computer to be that fast? So we don't really know what is quantum security strength. So it's really hard to ask people to move away from something which we don't have a concrete science, that is likely to be vulnerable, because we don't know how fast quantum computer was going to be or is going to be. We just don't know. We just don't know. So, but that's one point. The most important thing is we really would like to see the community to focus a lot more on quantum. It's very important to us right now, and we're very happy to see the community have been talking about this, and a lot of people working on it. And looking forward to see the finalized call for proposal from us in November, hopefully.
Great. You mean this November, as in like in a few weeks?
Yeah, this month.
Yeah, how much November is left?
Okay, just checking.
Cool, thank you.
I'm channeling the Java room again. If your large symmetric keys are not the result of your larger asymmetric operation, then what's the post QC benefit? Shouldn't this question be regarding asymmetric key sizes?
Asymmetric's the next slide.
Joe Mattsson.
Yeah,
yeah, follow up to, I would say that AES-128 would be fine even if you're using a post-quantum asymmetric key exchange like New Hoop. Even if somebody produces very fast quantum computers, they will not break AES-128 ever with Gruber's algorithm, as you cannot parallelize that. So if somebody using Gruber's algorithm, quantum computers to break AES-128, they will need to come up with some other algorithm than Gruber. And then we can speculate about other attacks as well. Yeah. But that said, 128-bit security, the overhead is quite negligible, so it might be reasonable to use it anyway, but I don't think people should be panicked to use it because of those quantum computers.
Kyle Rose. So if I recall correctly, that algorithm allows the operation to be performed in the square root of the time, right? So for 128-bit key, that would be 2 to the 64 operations. So I don't know if anyone can assert right now that a quantum computer powerful enough to be able to do that would also not be able to, that we'd also not be able to produce enough of them to do 2 to the 64 operations. I mean, it seems like you want a larger safety margin, which is the reason why 256-bit keys were recommended.
Safety margin is a great phrase. So, I mean, the newer analysis suggests that, AES, the 128-bit security level for symmetric crypto might be sufficient, and that would be awesome if it is. If other, if there's a community that feels that we need more safety margin, I would want to go with that. Let me move on to the next slide. So, it sounds to me like, there's not, trying to read the consensus of the room, there's not a lot of alarm that we need to use larger symmetric key sizes. In almost the opposite, right? That if we had to document like a recommendation, we would say, track things, come back to us next year, but don't worry about taking action this year. So for key establishment, we have, let's see, 2 basic approaches. One is, let's throw in a symmetric key into our key establishment algorithm as a way to get post-quantum security level. And that's what we're doing with IKE-v2. And so I actually put down this thing. It's not a working group draft, right? But is a draft that attempts to meet the requirements of the working group action item. And so this is a really simple approach, but of course it begs the question of, how did you establish a pre-shared secret in the first place? It's not really the way you want to do key establishment. So for the longer term, lattice-based cryptography is the interesting thing. And the So I'm a sci-fi person, not a fantasy person, but I like Frodo better than New Hope personally. Not that I have a lot of religion about lattice cryptography. So New Hope and Frodo are the two really interesting things in lattice-based cryptography. So New Hope is ring learning with error, and Frodo does away with the ring. And so Frodo, throw away the ring, right? If you don't know the joke, that's what the paper's called. So let's see. So Google did an implementation of New Hope in their Canary browser, and I asked Adam to speak to it a little bit, but he said, no, I'd rather actually sleep because I'm on the other side of the world. So, so he reports something like this, that their experiment with New Hope in their Canary browser has gone well, and that the additional latency from having to send another 2 kilobytes for every TLS handshake is noticeable in the tail cases, right? Not the average case, but in the tail. Noticeable, but if they had to live with this, they could. So that's really nice. Frodo puts even more data on the wire. The keys are larger, so that might be harder to live with. But there's fewer security assumptions with Frodo than with New Hope because there's less structure, right? The ring lattice has more structure. So if you're not following lattice key establishment, these are two things that look pretty encouraging, and they something else I didn't explicitly call out on the slide. There's an emerging consensus, I think, that when you're adding something like Frodo or New Hope into a protocol like TLS or IKE, the right way to do it is to say, I'm going to stick with my elliptic curve algorithm, and then I'm going to make a redundant system and add a lattice-based key establishment. So, because the last thing you want to do is move to a brand new thing that's not even secure against a classical computer, right? And these schemes are relatively new. So I think this is the state of the art for lattice. And I think what we're going to see is that New Hope and Frodo get implemented and probably tweaked, and certainly they're going to be cryptanalyzed. And in a few years, we'll have a much better notion of what kind of security level we can expect from them. So any questions or comments? Anybody has an opposing point of view on lattice crypto?
Yaron Schiffer, just to clarify what you just said, you're basically doing 2 handshakes and mixing the 2 into your session key?
Yes. Exactly, right? So it's like level of redundancy, right? You want to make it, and it's not hard to make it so that you essentially have 2 parallel key establishment schemes that if either one is secure, then you'd be secure.
Richard Barnes. So one of the things I've been looking for in this space is some sort of, like, someone to tell me a standard unified framework for doing that sort of combination. Has any work been done in that space?
That's a great question. I think, I don't think it's hard. And, something like the idea of a Diffie-Hellman group, the way, IKE did Diffie-Hellman groups, and then, you could make an elliptic curve group or an integer group. And so I think that's essentially the interface we want, but probably it can be done inside of the group definition, right? So for TLS or IKE, you could say, I have a group, and inside my group, it actually is doing both a lattice thing and an elliptic curve thing, and then you can kind of encapsulate it all there. It might be more awkward than you'd want, but I'm pretty sure that's doable and secure. Or maybe I'm wrong.
No, I believe that's what Chrome does now. I see David Benjamin there, so he can correct me, but my understanding is that Chrome has claims to be doing a Diffie-Hellman group, or an EC group, that is actually 25519 plus New Hope.
Perfect, thanks.
I was actually thinking of kind of a layer of abstraction up from that. You know, as we get these various proposals coming through, we might want to try various combinations of them and, you know, sort of mince new groups of this type to experiment with. It seems like that sort of experimentation would be a lot easier if there were a framework in which you could say, I'm going to plug this pre-existing group into this slot and this pre-existing group into this slot, and they'll come together and produce an output. You know, so just knowing the two inputs and the combination scheme, you can mint your new group that way. And it seems like there might be some good work to do in just like defining a standard for that combination scheme that we can all agree on, and then allow the innovation to happen at the input layer, at the specific key exchange layer, and not worry so much about the combination.
Yeah, I agree. That's interesting. And one wonders what the cipher suite combinatorial explosion would look like. But it seems like some good engineering could be done there.
So I think the draft you might be looking at, William White did a draft. I think that tried to figure out how to put some extensions to do this kind of stuff in TLS 1.2 and 1.3. It didn't really get anywhere in the working group, but maybe it'll come to life after this.
So, any other questions or comments? Any other bold opinions around key establishment? You know, I already talked about hash-based signatures, and that pretty much, you know, is the conversation around post-quantum signatures. Sorry.
They have to be bold.
Bold. They don't have to be bold.
So this is Debbie Cooley. I'm from NSA. Richard Barnes' question, can I push on that a little bit?
Yeah.
So do you mean actually exchanging the information or combining it once you get it? Like, what's the framework that's not completely protocol dependent?
So I think, you know, I'm in total agreement with what Ecker and David were saying about, you know, just treating these glued together key exchange mechanisms as just another group for purposes of things like TLS. I just think if we're going to go through a few iterations of the individual key exchanges that are going into these, it would be useful to have a standardized framework for minting these new groups. So I don't think it's probably protocol mechanics. I think this is more kind of ease of definition mechanics. So ease of describing your new group.
So just a way to talk about it.
Yeah.
Okay.
I mean, sort of like we have, you know, you say use TLS with this cipher suite and, you know, with this, you know, encryption algorithm, this key exchange algorithm, you know, it would be nice to be able to say use, you know, combined post-quantum, you know, combined key exchange algorithm with this key exchange algorithm, this key exchange algorithm.
So like you do with IKE and IPsec, right? So just say you want to use group, you know, 53 or whatever.
Yeah, except you say group 53 and 55, but maybe not in the protocol, maybe in the spec.
Right.
I mean, the most I'd be excited about doing here would be having some document that said, this is how you take a post-quantum, say you take a post-quantum thing and an ECC thing, which is say you HKDF them together and then allow code point registrations for the combination. What I'm certainly not prepared to do is have independent negotiation.
Absolutely.
Okay. Okay.
Look, I don't think this is challenging. I just think this is something that we need to write down or would be useful to write down.
Since we're in the realm of what would be useful to write down, what would be really useful would be if CFRG would give us some kind of read on whether any of these things actually are secure, even in the classical setting.
That's why we want redundancy.
I mean, it does seem that there's some serious questions about the security of these systems, or rather, serious levels of uncertainty about the security of these systems. It would be actually quite helpful if CFRG would attempt to produce some sort of document that said, you know, to the extent to which, you know, you want to experiment, we recommend you experiment with X rather than Y rather than Z. And here's why.
Does your proposal come with a time machine?
Well, I mean, if I did, then I would just do the work.
Okay, well, point taken.
Yeah, and to, you know, add a point onto what Richard was saying about it's not rocket science. It doesn't need to be big text, but just defining something would be nice. I also think, if we make a scheme or recommend a scheme that allows you to do 2 different key establishments, it'd be nice to describe. We're not trying to make this an open-ended stick your favorite key establishment scheme in here, so that we could have, say when you're operating across international borders, then each country gets to choose a scheme, right? That would be the hell we don't want to ever enter, right? So we'd want to make it clear we have an elliptic curve scheme and in a lattice scheme or something like that, right? So that and hopefully we'd have a very limited number of these things in there, and we're not just trying to make it a stick your favorite in here thing. So that wraps up for me. I have
a suggestion for that. So we had that same problem in TLS where the vanity crypto people showed up with lots of things, and so we recently added a recommended column, but that's more work on you as the CFRG to pick out what the actual recommendations are. So I'm looking forward to that work.
When does my cipher get in TLS?
Okay, I think. Oh, did you want to talk about last slide? All right, fine. Okay, thank you for coming. Just quickly, any other business, any quick announcements if you want? Yes, please add your name to the blue sheets so that we can get a bigger room, or at least keep the room of the same size next time.
Bring your protocols back. Somewhere in the building.